Welcome back to Learning as a Hobby. I'm going to go through the solutions to the selected exercises for section 3 in chapter 1 of Shifrin's multivariable mathematics in this video. So let me bring up my solutions and we'll go through them. So I wrote down in the video where I went over the summary, I showed all the problems that I did in this section, but we'll just go through them here. There's several of them. So we'll start with question number 3. Let me just move this out of the way. Question 3 says, suppose that x v1 through vk are vectors in Rn, and x is orthogonal to each of the vectors v1 through vk. Remember, orthogonal means that the dot product of those vectors is 0. All right, prove that x is orthogonal to any linear combination c1 v1 plus ... up to ck vk. All right, so here's the proof. Let x be orthogonal to each of those vectors vj for j1 through k, and we take the dot product of x with an arbitrary linear combination of them, and using the fact that the dot product distributes over vector sums, we can distribute the x to all the terms here in the sum. Right, and then there's also a property of the dot product that says you can switch the order of the products here. So this is the same thing as c1 x dot v1 plus all the way up to ck v x dot vk, and we know that x is orthogonal to each of the vj, right? So for example, x dot vi is 0, x dot v2 is 0, all the way up to x dot vk is 0. So we get c1 times 0 plus all the way up to ck times 0, which is all 0. So that when you add up k zeros, you still get 0. And that implies that x is orthogonal to the linear combination. And since the linear combination was arbitrary, it's orthogonal to any linear combination of them. Right, so that's question 3. Right, question 4. Actually, this was a proposition from the chapter section. So this proposition is there, but he asks us to prove it in the exercises, so that's what I'm doing here. So vperp, this is the proposition. Vperp is a subspace of Rn, so we show that it's a subspace by just showing it satisfies those 3 properties. All right, so number 1, we have to show that the 0 vector is in the set. When we take the dot product of the 0 vector with any vector, you get 0. So in particular, when you take the dot product of 0 with any vector in V, you get 0. And that implies that 0 is in vperp. Right? Property 2, take an arbitrary vector in vperp and take an arbitrary scalar c, and take the dot product of the scalar product c times x with any vector v in V. Again, you can switch the order of the scalar multiplication and the dot product. That's one of the properties. And you get c times x dot v, and x dot v is 0 because x is in vperp. So you get c times 0, which is 0, and that implies that c times x is an element of vperp. Right? And then same thing for addition. So property 3 says let x and y be arbitrary vectors in vperp, and consider x plus y dot product with v, where v is any vector in V. Right? Again, you can use the distributive law for the dot product. So x plus y dot v is the same thing as x dot v plus y dot v. And because x and y are in vperp, the dot products are both 0. So you get 0 plus 0, which is 0. So that shows that x plus y is in vperp. Right? So the 3 conditions are satisfied for it to be a subspace, and that means that it is. So that proves proposition 3.2. All right, question number 6. Part A, where did I? Yeah, there's multiple parts to this one. Part 6, part A says, let U and V be subspaces of Rn. Define U intersect V to be, well, hopefully you guys know what intersection means, but it's a set of all x that are common to U and V. Prove that U intersect V is a subspace of Rn, and give 2 examples. I didn't give examples, I just did the proof, but we can come up with some examples in a second. All right, so the proof, again, you just show that the three properties are satisfied. So property one, show that the zero vector is in the intersection, and that follows from the fact that u and v are already subspaces. So that means that the zero vector is in both of them, which means that it's in the intersection. Okay. Property two, take an arbitrary vector in the intersection of u and v. That means that x is in u, x is in v. Then for any scalar c, that means that c times x is in u and c times x is in v, because they're both subspaces, right? And that implies that cx is in the intersection. Right? And then lastly, property number three, let x and y be in the intersection of u and v. Then x, y are in u and x, y are in v. Again, because of the definition of intersection. If we take the sum, x plus y is in u since it's a subspace, and x plus y is in v because it's a subspace, that implies that x plus y is in the intersection, and that shows property three is satisfied. Right, so again, since the three properties are satisfied, it's a subspace. That's all you really have to do to show that it's a something is a subspace. Okay, what do they want? Oh, I wanted to come up with, he says come up with two examples. So I didn't write down examples here, but maybe I'll make up some two quick examples on the whiteboard. So for example, let u and v be the following subspaces of R. Let's do R3, I guess. So u is, let me think. Let's say that u is the set of vectors t e1 in where t varies over the real numbers. So that's basically the x-axis. And let's say that v is the subset t e1 plus s e2, for example, where ts are real numbers. All right, so this is the xy plane. This is the x-axis. Right, if you take u intersect v, you actually get, in this case, it doesn't always have to happen this way, but in this case, you get u. Right, so obviously it's a subspace. Oh, he said two examples. Do two examples. Let's do another one also. Let's say, actually do it. Let's do it in R4 then. Let's do u. So let u and v be the following subspaces of R4. So here we could let u equal, for example, TE1 plus SE2 for TS and R. And let's say V is RE2 plus KE3, I guess, where R, K, R, and R. Then if you look at U intersect V, you actually get the set, let's say TE2, T and R. And that's a subspace of R4. So just two, I mean, I just picked two easy examples. There's an infinite number of things you could pick. But all right, let me go back to the problems. Okay, we proved this. Part B says is U union V a subspace of Rn, and he wants us to give a proof or a counter example. It turns out that it's not a subspace, and so I gave a counter example. So if you look at these two subspaces, U, which is the span of E1, in other words, the x-axis, and V is the span of E2, which is the y-axis, then E1 is an element of the union and E2 is an element of the union, but E1 plus E2 is not an element of the union. Just to see geometrically why that is, I'll draw it in R2. Let's say that these are subspaces of R2. So the x-axis is span E1, the y-axis is span E2, and this is E1. Actually, let me do it in a different color so it shows up easier. This is E1. This is E2. So you can see that those two vectors are in the union of those two subspaces. However, if you take their sum, you get this vector, and notice that that vector is not on one of the two blue lines. So E1 plus E2 is not in span E1 union span E2. Right? In other words, it's not closed under addition. It's also, actually, it is closed under scalar multiplication, but it's addition that's the problem. Right? So that's part B. Part C, let U and V be subspaces of Rn. Define U plus V to be the set of all X in Rn. That is the sum that you can break up into a sum of two vectors U plus V for some U and V and some V and V. Prove that U plus V is a subspace of Rn and give two examples. All right, so again, to prove that it's a subspace, you just show that it satisfies the three properties. The zero vector is equal to zero plus the zero vector plus the zero vector, and the zero vectors in both U and V, so that works. Property number two, take an arbitrary vector in U plus V. That means that X is U plus V for some U and U and some V and V. Then if C is an arbitrary scalar, if you take C times X, that's equal to CU plus CV. And CU is in U because it's a subspace, and CV is in V because it's a subspace. Therefore, CX is in U plus V. Right? So it's closed under scalar multiples. And similar thing for vector addition. Let XY be elements of U plus V. Again, then that means that X is U1 plus V1, and Y is U2 plus V2 for some U1, U2 in U in the subspace U, and some V1, V2 in the subspace V. Excuse me. And if you take the sum X plus Y, that's equal to U1 V plus V1 plus U2 plus V2, and you can the vector addition is commutative, so you can rearrange things, and that gives you U1 plus U2 plus V1 plus V2, and U1 plus U2 is in U because it's a subspace, V1 plus V2 is in V because it's a subspace, therefore X plus Y is in U plus V, so the three conditions are satisfied. Okay, and he says give two examples again. I won't do two just because you guys can, come up with your own examples too. Maybe I'll do one though, just so we can see it. I'll define those on the whiteboard. So for example, let U, V be subspace, the following subspaces. In R3, I guess. So let's say that U is TE1, T in R, V is TE3. I'm just making something up here, T and R. And if you look at U plus V, this is the set of all TE1 plus SE2, E3, TS and R. And this is actually the XZ plane, which is a subspace, which you could check. Right? And you could come up, like in the other example, there's an infinite number of examples that you can come up with. That's just one of them. All right, back to the problems. Question number 8. Let V be a subset of Rn. Let V be a subspace of Rn. Prove that V intersect V perp is the trivial subspace, meaning it just contains a zero vector. All right, so here's the proof. Clearly, the zero vector is in V intersect V perp because they're both subspaces. We proved that in an earlier problem, right? V is a subspace, V perp is a subspace. So that means that the zero vector is in V, the zero vector is in V perp, so the zero vector is in their intersection, right? Also assume X is in another vector in V intersect V perp, where X is not the zero vector. So assume that there's something in the intersection other than the zero vector. Then again, X is in V and X is in V perp, just by the definition of the intersection. And that means that if you take X dot X, you should get 0, right? Because of the definition of V perp. But X is not the zero vector. So when you take X dot X, you get the length of X squared, which is not 0. And that's a contradiction. Therefore, the only thing that's in the intersection is the zero vector. All right, that's the proof of that. Okay, question number 9. Suppose UV are subspaces of Rn, and U is a subset of V, then prove that V perp is a subset of U perp. Okay, so here's the proof. Let UV be subspaces of Rn such that U is a subset of V. Let X be an element of V perp. Then, since X is in V perp, its dot product with any vector in U is 0, because U is a subset of V, and V perp is the set of all vectors that are orthogonal to V, right? So that shows that X is an element also of U perp, which means that it's that V perp is a subset of U perp since X was arbitrary. All right, that was question 9. Question 10. Let V be a subspace of Rn. Prove that V is a subset of V perp perp. And he asks, do you think more is true? All right, let's prove the statement first. Let V be a vector in V. Then for any U in V perp, just by definition, V dot U is equal to 0, which means that V is an element of V perp perp, right? That's by the definition of V perp perp, right? V perp perp is the set of all vectors that are perpendicular or that are orthogonal to the vectors in V perp, all right? So that shows that V is a subset of V perp perp, right? There is more that is true. In fact, V is equal to V perp perp. He doesn't say to prove it here, so I didn't. I'm assuming that either later on down the line we'll prove this, or actually I know for a fact that we're going to end up proving this statement in Axler in linear algebra done right. So I'll just say that it's true here, and we'll prove it later on. Okay, so number 11. I think this was the last one I did in this section. So suppose V is equal to span V1 through VK. Subset of Rn. Show that there are vectors W1 through WK in V that are mutually orthogonal, meaning that their dot product is 0. That's what orthogonal means whenever I is not J. That also spans V. And he gives a hint here. He says, let W1 equal V1. And using the techniques of section 2, specifically using projections, orthogonal projections, define W2 so that span W1, W2 is span V1, V2, and W1 dot W2 is 0, and then continue doing that. All right, so that's exactly what I did here. So choose W1 through WK thusly. So again, let W1 be V1, and then define WJ to be the orthogonal, what's the word? What you do is you project VJ onto the subspace V1 through VJ minus 1. Sorry, W1 through WJ minus 1. And that's what this is saying here. So these are all projections onto the other vectors that you defined to start with. So W1, W2, W3, etc. These are all the projections of V1 onto that. And then you take the difference, and that gives you the orthogonal vector to the projections. So just drawing a picture in R2, for example. Let's say we have these two vectors here, V1, V2. So we let V1 be W1, and then you take the projection of V2 onto V1, which looks like this. Whoops, sorry. So you take, so this vector here, this one here, is the projection of V2 onto V1, or sorry, into W1. That would be, by the formula we learned in the previous section, it would be V2 dot W1 over the length W1 squared, W1. And then to get this vector, you take V2 minus that projection. So minus V2 W1 over W1 squared, length W1 squared, W1. And that'll be W2, right? And you can keep going up and up and up like that. That's essentially what I'm saying here. That's what this construction is. All right. So that's how I'm defining them. And let me just show that this properties work that they ask us to have. All right, so span W1 through WK obviously is a subset of span V1 through VK because they're written in terms of V1 through VK, right? W1 is V1, and these are WJ is some linear combination of the VJs, right? So the span here is an subspace of a subset of the span here, and vice versa, because you can solve for VJ in terms of the W's. So for example, over here, okay, so VI is just WI plus these projections. So that shows that V span of V1 through VK is a subset of the span of W1 through WK. And lastly, WI dot WL is 0, since WJ was constructed to be orthogonal to the span of the previous vectors. So for each J, so they're all orthogonal, right? By the way we constructed them. And that's it. That was the last problem I think I did here in section 3. So I'll end the video here. And so again, thanks for watching, guys. The next video will be the next section in Simmons, the differential equations book. Then I got Taylor's book, the classical mechanics, and then we have linear algebra done right by Exler. So look out for those this weekend. I should be posting those within the next few days. So keep an eye out for those, and then we'll swing back around and do the loop all over again. All right, guys. So I'll see you in the next video. Don't forget to like and subscribe and keep learning.